So we've hopefully have learned about a very important rule for finding derivatives called the chain rule. And that's going to open up basically the rest of the derivative rules we need to learn for other functions. And one of the things we're going to look at today is implicit differentiation. But I just want to remind you of the chain rule again, because we'll be using it as we talk about what's known as implicit differentiation. So the chain rule says if I'm taking the derivative with respect to x of a composition of functions, say f of g of x, right? So we have one function inside of another function. G is the inner function, f is the outer function. Then the chain rule says this is the derivative of the outer function evaluated at the inner times the derivative of the inner function. And you really need to make sure you understand that process. It'll be used quite a bit from now on. Okay, so that's the chain rule. Again, the derivative of the outer function evaluate the inner times the derivative of the inner function. Again, the derivative of the inner function could involve all sorts of rules, product rule, quotient rule. Could involve the chain rule again. We can have a chain rule inside of a chain rule if the function g of x is the composition of more than two or more functions. Okay, so with that, let's talk about implicit differentiation. So up to this point, we've dealt with finding derivatives of functions that were given in what we say an explicit form, y equals a function of x. But some functions, however, are only implied, say, by an equation. Here's my example. The function y equal 1 over x, 1 divided by x, is implied in this equation x times y equal 1, right? I could solve for y in this equation by what? Dividing both sides by x. And so we say in this case, if you're given an equation, right, x and y are related to one another, obviously, right? The product x times y has to be equal to 1. So if x changes, if you increase x, you've got to change y accordingly so that the product is always equal to 1. And so we say that y is given implicitly in this equation. Now, this very simple equation I can easily solve for y. Look at this equation, though, involving x and y. Again, y is implicitly given as a function of x, right? In other words, the ordered pairs x, y that satisfy this pretty elaborate and crazy-looking equation, those ordered pairs, right, must satisfy this equation. So if I change any value of x, the corresponding value of y is going to change. Y is a function of x. However, it is extremely difficult, if not impossible, to solve for y explicitly as a function of x. However, we would still like to be able to talk about the derivative, right, of the function y. What is the derivative of y with respect to x in this case? And this equation, right, forms a relation, a set of ordered pairs x comma y that satisfy this equation. If we plot all those points, we get the curve of this relationship. Now, this relationship, y might not be a function of x only one time, and we'll explain what that means here in a minute. But there is a relationship, and therefore there's a graph that could conceivably be plotted and looked at, although it's extremely difficult in general to do that. Now, how do we find the derivative if we can't give y as a function of x explicitly? Well, that's this implicit differentiation process we're going to learn. And in this process, we think of y as a function of x. We don't know what y is as a function of x because we can't explicitly write it out that way. I can't write y as some function of x. I can't write y as x squared times sine of x or whatever it is. We don't know. We can't do that. I don't know what y equals in this equation. I can't solve for y explicitly in terms of x. So, but we do regard y as a function of x. So it's real important now when we do implicit differentiation that we think about what is the variable we're differentiating with respect to. What is our independent variable in this case? So here we say what the derivative with respect to x of x we know is 1. But now when I say what's the derivative with respect to x of y, notice y is not the same as x, right? But y is a function of x. This is not a constant. So the derivative with respect to x of y is not 0. It's not 1, but it's simply dy dx. It's the derivative of y with respect to x, or if we want to write it in the prime notation as y prime. The derivative with respect to x of x squared, well, that's easy. That's the power rule. Bring the 2 down, right? Subtract 1, we get 2x, so that's easy enough. But when I take the derivative with respect to x of y squared, what's going on here? Y is a function of x, right? Y is a function of x. Y is a function inside the squaring function. This is a composition of functions. So y is a function of x. That's the inner function. The outer function is y squared. So what we're going to use here is what? This is going to be the chain rule. And so the chain rule says take the derivative of the outer function. What's the outer function? Y squared. What's the derivative of y squared? Bring the 2 down, right? Subtract 1, I get 2y to the first power. Times what? Chain rule says what? Times the derivative of the inner function. The inner function is y. Its derivative is dy dx, as we just said above. So the answer to the derivative with respect to x of y squared is not 2y, but it's 2y dy dx, or 2y y prime, if we use the y prime notation. So you see the difference there. You've got to know what you're taking the derivative with respect to. Mostly my examples, it will be taking the derivative with respect to x. If you do some problems, say in the textbook or somewhere else, there may be other variables, so you do have to be careful. They change the variable. And so you have to be real aware of what you're taking the derivative with respect to, because that changes, right, depending on what you're taking the derivative of. Okay. Let's see how this works in an example that we can sort of see and contrast the two techniques. So the first, the equation I want to consider is this one, x squared plus y squared equals 1. So y is given implicitly here as a function of x. Most of you, I hope, recognize this relationship and what the graph looks like. This is actually the equation of a circle of radius 1 with center at the origin. This is the unit circle, sometimes called, with the center at the origin. And so in this case, we actually can solve explicitly for y. This equation is not that difficult to solve compared to the one that we were looking up here, which was much more complicated. This one we can't. So how do I do that? I subtract x squared, and then what do I do to solve for y? I take the square root. But when I do that, I have to consider what? Both the positive and negative roots. And so what we get here is y is actually expressed as not one, but two different functions. And that's what I was saying when I was saying up here that we think of y as being a function of x, but it might be several functions in a relation like this. And it's exactly two functions in this. The two functions are f of x equal the positive square root of 1 minus x squared, and then g of x is going to be the negative square root of 1 minus x squared. And if we look at this, then the f of x is basically the top half of the circle, and the g of x is the bottom half of the circle. So here's positive the square root of 1 minus x squared. Here's negative the square root of 1 minus x squared. And you understand, if we have a complete circle, if we put these two pieces together, we have the complete circle. But a circle, we can't express one function, y, as a function of x, because it would fail the vertical line test, right? We would have one input, say a half, which would give us two different outputs. So, but we can break it up into two functions. And that's what happens in a lot of these implicit relationships, these equations involving the two variables x and y, that we have y as a function of x, many different pieces, so to speak. Okay, all right, but here we can do it. Now we have explicitly given each function here, and we can now talk about finding the derivative. So let's suppose that we want to find the slope of the tangent line at the point in the square root of 3 over 2 comma 1/2. Okay, so first of all, where are we at? Square root of 3 comma 2, square root of 3 over 2 comma 1/2. Where is this point on the unit circle? Well, it's going to be on this one, right on the top half, because both x and y are positive. Y is a half, right? And x is the square root of 3 over 2. Okay, which is like 0.86 something, 87 something right down here. Okay, but that's that point right there that we're looking at. on the unit circle. And indeed, this x and y values will satisfy the original equation. If I go back to the original equation and square root of 3 over 2, I get 3/4. And if I square 1/2, I get 1/4. 3/4 plus 1/4 is indeed 1. Right? Satisfies the equation. That's what we mean by satisfying this equation. Instead of all points on this unit circle satisfy this equation. Now, something right away, we wanted the slope of the tangent line. You should be able to tell me something before we even begin about the slope of the tangent line. What can you tell me about the slope of the tangent line at that point? Think about what that looks like, the line that just sort of touches the graph locally at that point. I hope you're saying the slope has to be what? Negative. Has to be negative. Right? That slope is negative. We know that. Well, let's take a look and see what we get. I've got to use which function? This function, right? The top half function, f. And so I find the derivative actually by the chain rule. Notice that the square root of 1 minus x squared is the same as what? 1 minus x squared all to what? The 1/2 power. So there's a chain rule. I've got inner function is 1 minus x squared. Outer function is the square root of u, or u to the 1/2 power. So the derivative by the chain rule of f of x is u to the 1/2 is the outer function. Its derivative is 1/2, right? U to the negative 1/2, evaluated at u, which is 1 minus x squared, times the derivative of 1 minus x squared, which I hope everyone realizes is negative 2x. Right? And so 1 minus x squared to the negative 1/2 comes as 1 over the square root of 1 minus x squared, right? 1 minus x squared to the positive 1/2 down here. And then this negative 2 and this positive 1/2 become just negative 1. So I get negative x over the square root of 1 minus x squared. So there's the derivative given from the explicit form. Just the way we've been doing it. And now we can find the slope. Notice this is the x coordinate here. So I need to plug in x is square root of 3 over 2. And I've done that. And I did a little work to simplify and and finally I get to the result, which is good because we did expect the slope to be negative, and it is negative square root of 3, or about negative 0.8 something. Okay. So that's one way we could have done this problem, right? We have to know which function to use. Are we on the top half of the circle or the bottom half of the circle? Find the derivative and then plug in the x coordinate. Now I want to show you how to do this implicitly. So implicitly, we go back to the original equation, which was x squared equal 1, and we differentiate both sides of the equation with respect to x. Since both are equal, their derivatives should be equal. Now the derivative on the right-hand side is pretty easy. The derivative with respect to x of 1 is just what? That's 0. That's a constant. Here I have the sum rule, right? X squared plus y squared. Take the derivative with respect to x of x squared plus the derivative with respect to x of y squared. Now the derivative with respect to x of x squared, that's pretty easy. That's just 2x. But what's the derivative with respect to x of y squared? Remember, y is a function of x, right? We consider y as a function of x. In fact, we were able to explicitly solve for it above, but here we're assuming we don't know what it is. So it's chain rule, right? Inner function y, outer function y squared. Derivative is the derivative of the outer function 2y times the derivative of the inner function dy dx. Right? So what do I get here after I take the derivative implicitly? I get an equation, and you'll see in that equation dy dx. That is what we're looking for. What is the derivative? What is the derivative of y with respect to x? Well, here it is. So what we're going to do is algebraically solve for dy dx. Get it all by itself. And the way I do that is subtract this 2x and then divide by 2y. So when I subtract the 2x, I get here. When I divide both sides by 2y, the 2's cancel and I'm left with negative x divided by y. There's the derivative. Now something's different about this derivative than we're used to seeing, and that is the derivative of y with respect to x is in terms of not just x, but also y. Not just x, but also y. Right? Normally our derivatives are just in terms of the independent variable. Here the derivative is in terms of both the independent and dependent variables. And notice what this means. When we find the slope of the tangent line at square root of 3 over 2 comma 1/2, we have to plug in not only the x coordinate, square root of 3 over 2, but the y coordinate 1/2. So we evaluate. You remember how we evaluate with Leibniz notation? The derivative, this vertical bar means evaluated at, and we're evaluating at this point for x comma y. So x, right, is square root of 3 over 2, y is 1/2. I simplify, I get negative square root of 3, which is the same thing we got above, right? Obviously, we should get the same thing that we got above when we did it explicitly. So here was sort of to contrast the two methods to see how they work. Now, in this particular problem, we could have done it either way. But most of the examples we're going to look at, it's very difficult or impossible to solve explicitly for y. So in these cases, we have to really go with implicit differentiation. So that's what we want to look at. So before we do some examples, I just want to review some of the forms that will appear in the process of doing finding dy dx implicitly. And in each of these cases, recall that y is a function of x. Y is a function of x. So here's the first one. We've already seen this, right? The derivative with respect to x of y, that again is dy dx. Or we write y prime. Now I want you to make sure you don't do this. I've seen this before. This is not dy dx y like that. Notice there's a difference between d over dx y. This says take the derivative with respect to x of what's in the parentheses. That's what that says. The d over dx notation is indeed take the derivative with respect to x of whatever is in the parentheses. It's the differential operator. And so when we say dy dx, it's the same thing. This says take the derivative of y with respect to x. So these notations are really the same thing. But this says take the derivative of y with respect to x and then multiply it by the function y, which is typically not anything ever you normally want to be doing. This does not say take the derivative with respect to x of the function y. This says take the derivative of y with respect to x and multiply it by y. Okay. So I just wanted to clear that up. The derivative with respect to x of y to the sixth, chain rule. Y is a function of x, is the inner function. Outer function is y to the sixth. So by the power rule, derivative of the outer function, 6y to the fifth, times what? The derivative of the inner function, dy dx. Or if we were using the prime notation, 6y to the fifth y prime. I will sometimes use the y prime notation because it's just easier to deal with solving. But you can still use this notation. And in fact, sometimes this is important, especially if you have more than two variables going on or something, and later on we will need to do that. The Leibniz notation is very clear what we're taking the derivative with respect to. We kind of lose that information here. Right? We don't see any x's here. But most of the problems I have, y is just y and x are the only variables, and so this will work. But notice here, what's the change here? Take the derivative now with respect to y of x squared. So now the roles of the variables have changed. X is the dependent variable, y is the independent variable. So here we think of, before we were up there, we thought of y as a function of x. Now x is a function of y. Okay? And so in this case, the inner function is x, the outer function is x squared. Derivative is by the chain rule. Derivative of the outer function is 2x times the derivative of the inner function, which is dx dy. Okay? And that, so Leibniz notation is real important. You can see the dx dy is not the same as dy dx. Okay, it's not the same thing. Here I go back to the derivative with respect to x, sine of y. Y is a function of x. So by the chain rule, derivative of the outer function, sine, is cosine, if you remember, of y, times the derivative of the inner function, derivative of y with respect to x, is dy dx. Okay. Now, it's real important that this is cosine of y times this derivative function, so don't bring this inside the cosine function, the dy dx. In fact, sometimes you might see it written this way instead, just to make sure we don't do that. Or, if we use the prime notation, y prime cosine y. one looks very similar to what we just did, except it's sine of y squared. So if you think about it, we actually have the composition of three functions. Y is the innermost function. I then square that, and then I plug that into the sine function. So I actually have to use the chain rule twice. The outer function is sine. What's the derivative of sine? It's cosine. Evaluate at the inner function, which is y squared, times the derivative with respect to x of the inner function. Right, there's the chain rule. But now, when I take the derivative with respect to x of y squared, this is the chain rule, right? This says inner function y, outer function y squared. Derivative of y squared, 2y, times the derivative of the inner, dy dx. So it's chain rule twice. Chain rule twice. And so if I bring this 2y in front, I get 2y cosine of y squared times dy dx. One more, and then we'll stop this video. In the next video, we'll look at some more examples. Here we have what? Derivative with respect to x, x times y. So x is obviously a function of x, and y is a function of x. So if I'm multiplying two functions of x and finding their derivative, what rule do I have to use? Product rule. And the product rule says take the derivative of the first function, and in this case I'm going to emphasize with respect to x, times the other function, plus the first function times the derivative with respect to x of the second function. Now, the derivative with respect to x of x is just 1, right? But the derivative with respect to x of y is dy dx. And so I get 1 times y is y, plus x times dy dx. Or if you're using the prime notation, this becomes y plus x y prime. Okay, so those are some of the types of things we're going to encounter, and in the next video then we'll look at several examples to see how this all works in finding the derivative implicitly.